So my name is Tanya Birch. I'm a program manager at Google, and for the past several years, I've been working on this project called Dynamic World, which is a near real-time land cover data set. So just setting the stage, giving a little bit of background on the motivation for our production of this data set. The planet is hitting these two crises. One is climate change, and the other one is natural ecosystem loss and biodiversity, risks to biodiversity and extinction crises. So there was this Nature paper in 2021 that came out that said for the very first time, the Amazon forest is turning from a carbon, it emits more carbon than it sequesters, which is kind of a massive and scary thing. And we thought, okay, well, what can we do? How can we use our digital understanding of the physical world to catalyze environmental impact at scale using what Google knows about our planet? So in the meantime, we've been collecting data from satellites all over the world. This is just the Landsat collection. There's also Sentinel and a number of other data sets that we were bringing onto the Google Cloud and powering the Google Earth Engine platform with all of this data. So pairing satellite imagery with your algorithms to power real-world applications. And we thought, okay, well, what if there were a satellite that produced land cover data on the fly? And, at the same time, it was around 2018, we partnered with the National Geographic Society to build, to sort of build a vision around, okay, well, if we did this, who is going to use it? In this parallel meeting at the UN Convention on Biological Diversity is happening right now to understand, to set some ambitious targets around protecting 30% of the planet by 2030. So why land cover? Land cover is used in a number of different sectors, from water to energy to agriculture, ecosystems modeling and understanding biodiversity, but also a number of other sectors. And the data that, the state-of-the-art data was data sets like Copernicus, which, worldwide, once a year, 100-meter resolution. If you're in the US, you can benefit from an LCD once every 2 years, and that's becoming a higher and higher cadence. A lot of these data sets take a lot of manual effort to create and are therefore very, very precise, like an LCD. So we started to envision Dynamic World and what could that look like and how would we go about building it. And so we, again, with National Geographic Society and their network of aerial photo interpreters, we built a training data set because AI models are, as we've heard in many talks now, they're very data hungry. You need a lot of hand-labeled annotations to train an AI model. So on the top row of images, you're looking at Sentinel-2 scenes. The middle row of the middle strip of images, you're looking at how our annotators, expert annotators as well as crowd annotators, labeled the satellite imagery. And they labeled it in a taxonomy that was advised to us by the World Resources Institute, who we also partnered with on the Dynamic World project. And they took, they looked at the Lucas data set, they looked at the Anderson land cover labeling, and they decided to they advised us to stick with this top 9 land cover taxonomy. And then this little animation that you see here on the side is how we trained a model, an AI model. So how it works is you take some labeled data, water and trees, and then you feed it into an AI model. And an AI model begins to learn and recognize what those patterns on the landscape are. And then you show it an unseen image. And if you did a good job, if the model really learned well, then it makes a classification on what the land cover would be. And unfortunately, this does work. Look at that, my animation works. So now what we're producing is as Sentinel-2 data comes in from the cloud and comes in from to the ground station, we upload it to the Google Cloud, and then we run it through our AI model and produce this parallel image collection for any Landsat, any Sentinel-2 scene that's less than 35% cloudy. So there is this sort of new concept of this near real-time land cover data set that's this parallel image collection in Earth Engine that's freely available to anybody. So that's dynamic world. Again, just to reiterate, it's 10-meter resolution. It's based on European Space Agency Sentinel-2. Thank goodness that's freely available, because that's something that we can then build upon with these sort of research efforts. And it has near real time, the same revisit rate as Sentinel-2 does. It's freely and openly accessible. Both the AI model, everything that went into the production of this is intended to be reproducible. And our peer-reviewed science paper came out in June of this year. So this is what the data set looks like. This is actually an annual squash of the data set in Ho Chi Minh City in Vietnam. This image is, like, I think, one of my favorites because it's just incredibly beautiful. You look at the Mekong Delta, there's a lot of land that's used for aquaculture and rice paddies, and you can see some of the seasonal differences depending on the period of time that you look at the data. It's also a massive data set, so last time I checked, it was over 10 petabytes running forwards, so it's continually running forwards. We also ran the model backwards in time to the beginning of the Sentinel-2 collection, L1C collection, and there's a new dynamic world scene getting produced every 14 seconds or so. About the accuracy, so again, it's kind of hard to validate the accuracy of a near real-time project without doing so derivatives should really be using a design-based analysis to understand the downstream accuracy of a derivative product. But we had taken 409 tiles from the annotators and held those back for validation. And what we're looking at is a confusion matrix of these dynamic world to an expert consensus where at least 2 experts labeled and they all agreed. And that's sort of our final metric for precision or user's accuracy is 73.8%. But again, it's highly variable, right? These are looking at top 1 predictions, and I'll get into a little bit of, I think, the true value of this data set in a second. We also compared against other popular or local regional land use land cover maps against this 409 holdout set, and found that it performed on par or exceeding some of the most popular land cover data sets around. However, this is one of the main takeaways is it is not a static map, right? If you're looking for an off-the-shelf static map, you're probably better off with ESA World Cover. We presented with them at AGU last year. This is really an excellent product at an annual cadence. They have a 2021 data set. It's also in the Google Earth Engine catalog. So I mentioned a little bit about the output of dynamic world. So it's per pixel probabilities across 9 classes. And here we're looking at a single scene over Hungary. So I want to sort of spell out a little bit of what I mean. So if I were to just take a single pixel in the center, I can see the probability distribution across all 9 classes. And for this specific pixel, it's predicting trees at 23% and crops at 41%. And that is for every single pixel for the entire Sentinel-2 catalog across these 9 classes, right? And so where we find it can be useful is for pulling out, this is just taking the crop value and mapping the crops across the high probability of, or the probability of crops across the landscape. And then this is just taking the tree signal and mapping the treeness of an area. So again, like if you think about, you know, what's outside, and you imagine like a 10 meter by 10 meter block of, you know, space outside, you know, AGU, it's probably not a single label, right? It's probably a combination of different land cover classes. And so we're excited about Dynamic World because we think that it more accurately represents the landscape as it really is in the world. The other thing that we did was, this is dynamic, you can see the sort of changes over time. So we took that probability space and mapped it to a hillshade effect so that you can see the areas of high probability sort of pop out on the map. But it also pulls out artifacts like this power line that cuts through the forest. The power line has a lower probability for trees, so it looks, you can actually see that through the visualization of this hillshade effect. And that's the default way. If you go to the Google Earth Engine data catalog for Dynamic World, that's the default way that you can visualize Dynamic World. So again, the sort of three main innovations of Dynamic World are this near real-time image classification for every Sentinel-2 scene coming in, time series class of probabilities that allow you to look at intra-annual change or very timely events like landslides or floods or you know, disasters, or things like cover crops, right? If you're looking at cover crop change over time. And then the third one is it's really powerful for derivative map products, right? Because this is where we sort of came up with this like informal slogan, map with you, not for you. We really want to enable the ecosystem of Earth Engine users to take this data set as an input, and you can even use it as an input for other training data and train a random forest classifier on top of that and then output a derivative map. So here's our Nature Scientific Data paper. We're still, you know, knock on wood, on the homepage of Nature Scientific Data, so that makes the URL mapping really easy. And then you can explore the data on a user-friendly website, or if you want to dig deep into the time series, I'd recommend this Dynamic World app URL at the bottom. But it's also in the Earth Engine data catalog, along with the ESA World Cover dataset, and a number of other land cover data sets if you want to do your own analyses or comparisons. So this is, again, I mentioned this a second ago, but this is my favorite way to explore Dynamic World is this bit.ly/Dynamic World app, because you can see, I don't know if I have a mouse, I do have a mouse. Okay, so you can see the time series of a single pixel. Like I clicked right over here, and I can see that in March, that pixel was classified as snow, and later on, the rest of the year, that the highest probability is for trees. So with a little bit of, you know, uncertainty right around the area where the snow melts and, you know, we start to see some leaf on. But this seasonal aspect is I think the real, you know, one of the real values of Dynamic World. So the last thing I want to show is an example of how an organization, an NGO, is using Dynamic World in an application for change detection. And again, like change detection is a whole field unto itself, right? They're just looking at basic pixel state change for Amazon mining. This is alerts.skytruth.org, and if you go there, you can see underneath layers, there's Dynamic World. And I'm going to highlight a spot in Peru, because this is where they're looking at Amazon gold mining, change detection. And I also, I'm showing this example because they've trained a custom machine learning model to detect gold mining. And so that provides fertile ground to compare it against Dynamic World outputs. And they have a, you know, kind of like a baseline. So you selected a date range, 2019, June to September 2019, and then also 2022. And you can filter by land classifications, and I'm going to show bare ground, new bare ground, because this is the kind of, Amazon mines we detected as bare ground, or mines, not any mine, not just in the Amazon. And then you can define a change threshold, or filter by a threshold of change. We'll say 25% change. And we're looking at the planet base map for high resolution data to compare against, or to ground truth. And this is, so 10% and 40%. So you can also move, shift along the probability space and the confidence in that probability. And this is, we're just going to stick to 25 for this example. And then I can also say that because, there's more uncertainty in some of these riverine areas, I can pull out the water signal. And the takeaway for this one is the gold mining specific ML model clearly outperformed dynamic world as predicting and finding, doing change detection for gold. But you would expect that, right? Because it's using local data, it's refined, it took them months to build. What they did in dynamic world took them about, well, I shouldn't overestimate, took them about a month or so to put together. But the dynamic world data was just ready for them to use and build these toggles upon. So that's kind of the big thing, right? If you want to build something that's very, very precise and very custom, you're better off building something that's bespoke, using bespoke training data. But dynamic world can get you quite far along the way, depending on what you're looking for. So that's that website again, if you want to check it out and play with it. I also want to just make a couple final plugs to some resources on how to get started learning about it and using it beyond the paper itself. So this is somebody in our Earth Engine developer or our community that is Ujjwal Gandhi. He's written 3 tutorials on just getting familiarized with dynamic world in the Google Earth Engine environment. And we taught a course. It's a free AGU workshop. There's a lot of really fun, interactive ways that you can explore dynamic world in a Jupyter notebook in the Colab environment. And you don't need technical expertise. I promise you, you don't need to know how to code to follow this this workshop. It's really neat. It's really fun. You just need to get past Google authentication. So a couple other resources, dynamicworld.app, the bit.ly site that I linked to, and then a whole host of resources for Earth Engine. I think that's all. The one last plug is it's a new data set. We're really excited to see how people use it and hear from the community. So if you have if you've started using it, or you have something that you are building and you're using Dynamic World, email me, tell me about it. I would love to hear how we can support and accelerate your work. Thank you.